The way in which magmas evolve during differentiation and the causes for magmatic diversity are critical questions in the field of igneous petrology. In particular, there are two end-member differentiation trends: the phylitic trend, which is characterized by an iron enrichment, and the iron-depleted calc-alkaline trend. However, many questions remain as to their exact causes. Although Calc-Alkaline differentiation trends are ubiquitously associated with subduction zones, many arcs, including the Aleutians, erupt Calc-Alkaline, intermediate, and phylitic magmas, and even single arc volcanoes also erupt Calc-Alkaline and phylitic magmas, such as seen in Newberry Volcano. While experiments suggest a correlation between high water content and calc-alkaline differentiation, few studies have assessed the specific role of oxygen fugacity independent of water content. Thus, the relative importance of oxidizing versus hydrous conditions in producing calc-alkaline trends has not been well established. Often, experiments like the one shown here are conducted at several water contents and/or several oxidative conditions, making it difficult to investigate the sensitivity of these liquid lines of descent to very small changes in water content and oxygen fugacity over a wide range of values. To address this fundamental petrologic question, we used a Monte Carlo approach in which we modeled using rhyolite melts the differentiation of 8 parental compositions from 4 volcanoes, including the strongly phylitic Thingmilli shown in red and up to the strongly calc-alkaline Augustine shown here in green. For each of these parental compositions, we modeled 1,000 to 2,500 rhyolite melts runs using water contents of 0.1 to 6 weight%. And for each of those water contents, we varied the oxygen fugacity from FMQ-1 to FMQ+3, shown by the color bar in this animation. You can see that as we're increasing the water content and changing the oxygen fugacity at each of those water contents, the liquid line of descent varies significantly. We also, for each one of these compositions, vary the pressure by 100 to 500 megapascals. In order to quantify the degree of iron enrichment, we created a brand new phylitic index, which involves the initial iron content, the maximum iron, and the iron at magnesium oxide equals 4. In this phylitic index, anything higher than 1 is a phylitic trend, anything lower than 1 is calc-alkaline. And in this particular model run, you can see that the phylitic index of 1.4 indicates that it's highly phylitic. We find that this performs significantly better than the Zimmer et al. 2010 phylitic index, and I would be happy to discuss that further in the question and answer time. So to investigate liquid lines of descent sensitivity to water and oxygen fugacity, we first calculated the phylitic index of every melts run. Then we could plot that phylitic index against the oxygen fugacity and water content of that particular run, fit a surface to that, create contours, and then eventually get this contour map that allows us to see the regions that are the most phylitic and most calc-alkaline in water and oxygen fugacity space. Notice that the range in phylitic index for the high iron parent, that is Thingmilli, is much larger range than for the low iron Augustine parent. And this is captured in these contour maps here, where you can see that in order to get a highly phylitic differentiation trend shown by the dark red requires not only low water content and reducing conditions, but also a high iron parent. As you can see, there's no dark red region in the Augustine starting composition. In addition, you can see that at oxidizing conditions over FMQ plus 1.5, regardless of the water content, you'll get a strongly calc-alkaline differentiation trend. And this happens regardless of the parental composition as well. Finally, you can notice that at oxygen fugacity of FMQ and above water contents of 1, for a given oxygen fugacity, changing the water content does not change the phylitic index of the liquid line of descent, indicating that these differentiation trends are not sensitive to changes in water content in these conditions. Finally, you'll notice that for the low iron parent of Augustine, any water content greater than 0.5 will lead to a calc-alkaline differentiation. So to investigate the effect of those parental compositions, we can take the fulleatic index at each point on this figure, subtract it from the fulleatic index of each point using the Augustine data, and that gives us this figure here, where the region in white indicates that the Thingmilly and Augustine fulleatic index are the same. And this region of dark red indicates that Thingmilly, the fulleatic-like parent, will lead to a much more fulleatic liquid line of descent, given these conditions. Perhaps more surprisingly, even the fulleatic-like parent, the Thingmilly parent, will evolve to a more calc-alkaline liquid line of descent than if we had started with the calc-alkaline Augustine parent. So, keeping this in mind, we should avoid using the terms fulleatic or calc-alkaline to describe the parent alone and save this only for the trends. Note that these trends are observed regardless of which high iron fulleatic-like parent and low iron calc-alkaline-like parent that we use. We also investigated the effect of pressure, and you can see that as we increase from 100 megapascals to 200 to 300, it has very little effect on the liquid lines of descent, indicating that there's low sensitivity to pressure compared to water content and oxygen fugacity. However, at high pressures like 500 megapascals, the behavior becomes significantly different due to the stability of pelagic glaze. So in addition to looking at the iron enrichment, we can also look at the goodness of fit of the model runs to the observed data. We first convert all of the major elements to z-scores, then calculate the multivariate sum of squared differences, indicating that these small values of SSD are the best fit indicated by the dark colors. And you can see that we can fit a surface and create contours that indicate the regions of best fit to the data. On the starting composition, the regions of best fit and the sensitivity to both oxygen fugacity and water content are vastly different. To look at this sensitivity closer, we have sum of squared differences versus oxygen fugacity, and you can see that for a given oxygen fugacity, if we allow water content to vary over the entire range of our models, the change in goodness of fit is 45. However, if we hold water content constant and allow oxygen fugacity to vary, the change in goodness of fit is doubled, indicating a much greater sensitivity to oxygen fugacity. However, this may not always be the case depending on the composition and pressure. The range in SSD due to oxygen fugacity divided by the range in SSD due to water, such that values greater than 1 indicate a greater sensitivity to oxygen fugacity than for water. And you can see for all of the systems and for all of the pressures, these tend to be much more sensitive to oxygen fugacity than to water. Thus, I leave you with these conclusions, and I look forward to answering any questions that you may have. Thank you so much.